So in this next section, we're going to talk about one specific realization technology based on something you know pretty well, which is microstrip line technology. And I'll show you a good set of improvements that this author here did several years ago, Andy Brown. And the main schematic that I want you to focus on is shown essentially in this figure right here. So this is something, again, that should look very familiar. This is the center conductor of a microstrip line. So in reality, really, you have a microstrip line resonator. And remember that if you have lambda by 4 or lambda by 2 resonators, you can essentially make filters. But he has made several steps to improve the quality factor to actually a heroic quality factor. First of all, he made sure that this W is quite wide. In fact, you will see later on that we're talking about widths in the order of 700 micrometers, which essentially are made specifically to reduce ohmic losses. The second thing is that, as you will see, the substrate here has been etched away. This was a technology that was meant for silicon substrate, and as you can imagine, silicon is a semiconductor and therefore can be quite lossy. And this is a high-frequency design, so the filter examples you will see from here are basically in the order of 30 to 60 gigahertz. And when you do frequencies like this, even a little bit of dielectric loss can be quite detrimental. So there was a huge desire to remove the substrate. And it's actually because of removing the substrate now that you can essentially have to increase the W even more, because the impedance essentially will be affected by that. Now, when you do those two things, you have to worry about radiation. And so what he's also doing here is that he's basically capturing the structure within a fully metallic package. By the way, the substrate is on this side. I made a mistake. And this side of the house is basically the package to remove radiation. You will see here some via holes that have been created to make the package, and you also need now to bond 2 wafers. Now, bonding is easier said than done. Depending on the technology you have at hand, it may actually be quite difficult to do. And in this particular case, there was a technique applied, thermocompression bonding, which essentially bonds 2 metals together by essentially applying heat and pressure. So it's a very interesting technology, quite involved. But if you're willing to go through this pain, then you can actually go from a Q of 50 to a Q of 500, which is basically a 10x improvement. And that's quite amazing that he was able to get a Q of basically 500 even with just a microstrip line. But it shows you, and that's why I'm putting this image here, that once you understand what limits your Q, you can very quickly go a step-by-step approach and essentially improve it from something that is useless, 50, to something that can actually become useful, which is 500. So here's some simulation examples using essentially electromagnetic solvers. So this is the unloaded Q as a function of the conductor width, so as a function of W. And it's actually done for different substrate heights. So this is a substrate height of 30 micrometers, substrate height of 200. The details are not too important for our class, but what is important to note here is that there is a clear tendency that the wider you make your line, the lower the ohmic loss will be. And as long as you can control the radiation, which he is doing here, you will actually get a higher Q. This is the actual measurement result. This is the actual resonator that Andy built. And you can see that he was able to get a Q of about 450 or so at 30 gigahertz. He also did exactly the same thing at 60 gigahertz, and here he was able to get even higher measurements, essentially Qs that are almost 500. Same idea, same trends apply here. This is a detailed table. This is mostly up to you if you would like to compare different solvers with different approximations. And I don't think we should talk too much about this. I also wanted to, I think it's more useful if we talk a little bit about practical realization of this. So first of all, let's focus on this first picture here. And let's try to look at this layout and relate it to what we have learned. So the first question you should be asking yourself once you see such a layout is the following. How many poles do I have? What's the order of the filter? It's actually easy to answer this question simply by counting how many resonators you have. Here are the microstrip resonators, 1, 2, 3, and 4. So essentially you have fourth order bandpass filter here. This filter follows the approach that we have seen. It's basically an edge coupled filter. So by controlling this gap here between the resonators, you're basically controlling the capacitance coupling, the capacitive coupling between the resonators. So this is basically an edge coupled filter. This is the filter that we have basically designed in detail just a couple of lectures ago. Also notice that this is the input here and this is the output. And because the coupling between the input transmission line is not as strong as between those resonators, and because the coupling coefficient is higher, instead of doing edge coupling, he has actually done this coupling here where he's brought the lines very close to each other. The idea is exactly the same. He's simply increasing the overlap width, if you will, to basically get a higher coupling coefficient and essentially get the right inverting value. This is going to be the inverted J01, for example, for the input. The other things that are less important, but I just want to explain this layout a little bit, is these black lines here that you will see. These are basically the via holes I mentioned before. So not only he is packaging this filter from top to bottom, but he's also making sure that this filter is isolated from neighboring structures. Also, those vias eliminate surface waves. One of the dangers in real life design, when you basically excite a filter in a microstrip or in any other mode, is essentially launching accidentally surface waves, and those via guards are basically going to kill those. Finally, I also want you to look at one little detail here. This little detail basically is related to the widths that you will see between the input line and resonator 1. You will see that this width here is actually different than this width, and that's something we discussed before. Your width for your resonators doesn't have to be 50 ohms or anything like that. It's actually whatever it needs to be to maximize the quality factor. Now, if you were to fabricate this filter, and Andy actually fabricated this, and if you were able to compare your measurements and simulated results, you would have some good news and some bad news. So the good news that Andy had is that even though he made the fourth order filter, which again it's pretty sharp, he was able to get essentially insertion loss that was basically around 1 dB. So the insertion loss is actually shown right here. It's a very good insertion loss, and this insertion loss would have been actually over 10 dB if he had not improved the Q to the order of being about 500. Now, the not so good news is what happens relatively far away from your passband. If you see this blue line, essentially it kind of saturates. So you can see that it basically goes very sharp as it should be, but then suddenly, for example, on the left-hand side, it will saturate between 30 to 40 dBs. Here it will saturate in the order of 40 dBs or so, but it won't keep going down. The theoretical simulated filter is this red line, and in theory, this filter should basically go all the way down. So why is this happening? Well, it's happening because of the unwanted couplings that I had mentioned to you before. Just because we have modeled this structure that you see here with a microstrip edge filter, it doesn't mean that this is the only thing that's happening here. There is still unwanted coupling between the input and the output. And this coupling is actually realized through multiple ways. It's realized through, for example, air coupling, is realized through unwanted modes that are still excited in the structure, is realized through, for example, the measurement apparatus. The point is, because you have this inline structure, the filter performance is very good within the passband, but it actually suffers once it goes away. Andy really wanted to hit, rejections levels in the order of 70 or 80 dBs. So the way he was able to do this is by this ingenious structure of basically the bent filter. And you can see how, again, theory and practice are a little bit different. That bent filter, it now doesn't, the input and the output are not literally face to face. So the coupling between unwanted modes is greatly reduced. And that essentially is what led to this black structure here where essentially it follows simulation all the way down to the 70 to 80 dB level. And this filter is a heroic result. And I'm showing it to you, obviously as a tribute to Andy, which at the time was advised by Professor Abbase, but also so you can essentially think and ask the right questions. When you get a result like this blue line here, what might have caused this, and not simply give up and say, well, that's the best that can be done. Very quickly, he did exactly the same thing at different frequencies. So this is another example following exactly the same ideas. And finally, he put the two together to realize a diplexer. So this is a diplexer with two different filters. Here's the filter, the first filter. Here's the second filter. And you can basically get a very nice diplexer where it has very high isolation between the two bands.